I'll give you a minute to write this sort of like a summary of most of the things we'll do in this module. My original plan today was to go over that exercise of predicting the odds of the election, but I want to push it back to the last lecture on this topic. First, discuss all the concepts that I want to get through before we do that. Okay. So, until so far, we have seen what are random variables which can be either discrete or continuous. Last two lectures have been, the discussion has been around discrete random variables, which are non-negative integers. So things that you can actually count. We saw the binomial distribution, which describes the outcomes in experiments where there are only two outcomes possible, like head or tail, boy or girl, those kind of situations. We also saw the uniform random variable, which describes outcomes in instances where all the outcomes are equally likely, like the sides of a dice. All the sides are equally likely. So the chance of any one is just 1 divided by the total number of outcomes. We also saw the Poisson distribution, which describes the probability of a rare event happening a specific number of times with a given value or average mean value for the quantity. Like whenever you think of Poisson distribution, I want you to think about my example related to earthquakes. The chance of earthquakes in San Francisco is or Los Angeles is 1 in 30 years. What is my chance if I live there for 30 years? How many quakes or so what is the chance of experiencing exactly 0 quakes, exactly 1 quake, 2 quakes, and so on? That is given by Poisson distribution. We saw these 3 types of discrete distributions, and don't think that these are the only 3 types. There are many more types of distributions that are there. In our course, we are seeing only 3 of these. We also saw concepts of what is probability. Can you tell me what is the probability of a certain event occurring? How will you define it? What is P of xi? How do you calculate P of xi? It is the number of outcomes favorable to that event divided by the total number of outcomes. So example is, if what is the chance of getting a red colored card in a stack of playing cards? 50%, because there are 26 cards of either color out of 52 cards, which makes the odds 1/2. Okay, so P of xi probability is the number of outcomes favorable to that outcome or that define that outcome divided by the total number of possible outcomes. Okay, and cumulative probability is the sum of the probabilities until a particular value. Like for example, if I say for a dice, what is f of x3? What is the chance of getting everything up to 3? So I equals 1 to 3 p of xi, which is 1/6 plus 1/6 plus 1/6. This 1/6 is the chance of getting a 1. This 1/6 is the chance of getting a 2. This is the chance of getting a 3, which will make this 1/2. So as far as discrete distributions are concerned, this right here has all the information you need to solve problems if you know what you're doing. Okay, I'll give you a moment to write it. So today I'm planning to talk about continuous random variables, but before I do that, I want to ask a question and want an answer from all of you. If you are given a data set meaning a long list of numbers or a long list of outcomes. So data set could mean, need a new marker. So when I say data set could imply if it's a discrete random variable, it could be a list of outcomes, a list of possible outcomes, or a list of outcomes like a survey or like a coin flip done like 1,000 times. It's a sequence of head, tail, and so on. Or it could be a list of numbers which denote the quantity. Suppose you are doing a voltage measurement, which is a continuous random variable. It could be about 1,000 values of voltages acquired in a measurement. How do you first determine which type of distribution is the underlying pattern for that random variable? How do you do that? You have a list of 1,000 numbers. How do you know whether it follows uniform distribution or Gaussian distribution or Poisson or whatever? What is the first step in all of your statistical analysis? Yeah. Graph it meaning?
You can look at the curve.
What curve?
The trend that the data follows.
You're telling words that individually make sense, but you're not putting them together.
Like you can, in MATLAB, you can put the numbers in, you can generate random numbers and look at the Poisson distribution.
No. So right now I'm not making any preconceived notion that it follows Poisson or whatever distribution. All I am giving you is a list of 1,000 numbers. How will you determine what is the underlying distribution? The basic act which we talked about in the first lecture, you have a list of 1,000 numbers. Where do you start? Do the histogram. So the answer is you start with the histogram. And what is the histogram to refresh ourselves?
The distribution, data, organized.
Organized or binned data.
Yeah.
So when you say data set, like a list of numbers, this is called raw data. And the histogram is binned or processed data. So if you have those 1,000 numbers, instead of walking around with a stack of 1,000 numbers, you create ranges and put how many types of numbers or how many numbers are in each range. Between, say, for example, if the 1,000 numbers have a mean of let's say around 500, you can create bins that are of width 50 and ask the question, how many are between 450 and 500? How many are between 500 and 550? How many are between 550 and 600 and so on and so forth. So you bin the data. The keyword here is bin. Literally binning, carrying your laundry and putting it in your bin. Remember the act. You're sorting your stuff. Okay. So you look at the histogram. And the shape of the histogram is the mathematical name for the shape of the histogram is distribution. The shape of the histogram is fitted to a mathematical function which we call distribution. Okay. Again, please write these things down. Very important. All right. So in principle, you get a data set, you do the histogram, and you get the distribution. In practice, you can use MATLAB, and this is where the tool I showed you, distribution fitter app. Distribution fitter or fitting, I forget, fitter app. If you go back and watch last lecture's recording, we would have showed how to use the distribution fitter app, how to import your data, how to do this in MATLAB. If amongst us there are Python experts who know Python better than MATLAB, The same ideas apply, but the syntax will slightly change. It's just a matter of language. But I showed you an example in math. So if you get a data set, you pull it into MATLAB, you look at the histogram, and then you can fit different distributions and see which one gets you the best fit. Okay. Once the distribution is known, other statistical measures can be readily computed, and you can generate more random numbers, generate more random numbers. I shouldn't say more, I should say additional random numbers that follow a given distribution. Sorry, it's going very below, but I'll stop. Once the distribution is known, you can generate more random numbers or basically make up more numbers that follow the same pattern. Okay. We also saw that in last lecture, generating binomial random numbers or Poisson random numbers and so on. Up to this point, that is basically this discrete random variables and the basic idea of handling data sets. Any questions? Okay, we'll do some MATLAB today also at the end of towards the end of the lecture. All right, so let's get to the today's topic, continuous random variables. Can I erase this? Yes.
Sorry to answer earlier, but what do you mean by student?
Student's t distribution is a name. It's one of the distributions that we will discuss. Yeah, it's the name of the distribution. All right. So we'll start with the concepts. Okay. So when we talk about continuous random variables, okay, the word continuous is important. We are talking about a quantity which is not an integer, like a velocity or a temperature or something. Okay. Something that's usually measurable. So when we say, for example, when we have a list of data and we are trying to bin them, suppose our sequence of data is 1000 voltage readings. For example, 1.000 millivolt, 0.997 millivolt, 1.312, 1.014, 0.987, and so on and so forth, like 1000 values. In reality, you can acquire as many values as you want. You could acquire 100,000 or 10 billion for all you care. This is just a sample out of a population. So the first terminology we are introducing is population and sample. What is population? All the possible outcomes or values. And sample is the ones that were acquired or discovered during a trial or experiment. Okay. Usually you can never access the entire population. The population is always usually a large group. It's almost impossible to get to everyone. That is why when they do polling, they ask about 1000 people or 10,000 people instead of polling the entire population of a state or a country, which is impossible. So sample is what we usually work with, even though population is what we want to capture. Okay. All right. So when it comes to continuous random variables, you saw what is probability for discrete variables. What is the probability, or how will you define probability for discrete variables? Probability of xi is what? It is the number of outcomes favorable to xi divided by the total number of trials or outcomes. Okay. In here, that is for continuous variables. For continuous variables, we define the probability of x of the we define the probability of the random variable taking a value between x and x plus dx as f of x dx. That's a very awkward sentence to write. We define the probability of a random variable assuming a certain value or assuming a value in a certain range to be as f of x dx. It's almost like saying if here is x and here is x plus dx, okay, and here is f of x. So this length is basically dx. This length is dx. It's almost like saying f of x dx is the probability, or f of x is a probability density. Probability density. What do I mean by density? Like, what is your interpretation of the way I've written it? What is density, generally speaking? What are the densities that you know of?
The amount of something in a given space.
So you know the density, which is the mass density per volume, right? Mass per volume. If I tell you the density of the air in this room and ask you for the total mass, you very well know this multiplied by volume gets you that. Okay. Or if we make a very weird calculation, what is the average density of this room considering the air, the benches, and us? What would be that calculation? Look, it will be the mass of all the humans plus mass of all the furniture plus mass of all the air divided by the volume of the room. This will be like sort of an average density. Except, you know for a fact, even though we are all here, but the volume is mostly due to the space and not due to us. And the mass contribution, even though we are all here, air is much more in quantity than us. If you actually weigh the amount of air here. So this is heavily weighted towards this. Okay. So the idea is a density times volume gets you a quantity. A density. I'm not saying mass density, A density. Suppose you have heard of population density, right? Like the total number of people in a geographic region divided by the area, that will give you persons per square mile times area will give you the total population. In the same sense, when I write f of x dx and call f of x to be a probability density, it is like saying it is the probability per unit length. If x is my quantity, if the x is of length dx, or in the other words, if x varies over dx, the probability is f of x dx. Let me ask you a question. When you have a range of voltage values that you acquired in measurement, what is the probability that this voltage will assume exactly 1 volt? Not 1.000, but exactly 1 volt. It's not just very low, it's actually 0, because a real world quantity cannot be precisely equal to 1. When you try to measure it, even if it is 1, you will never uncover it, and even if you're able to measure it, it won't be 1. So if I say the probability of x assuming equal to 1, okay, the probability of x equal to x naught is f of x dx, okay, where dx equal to 0. Meaning, if I just want x naught, if I just want x naught, I don't have any area. All I have is dx equal to 0. The probability is also 0. So by extension, if I say, what is the probability of x lying between A to B? What would you say? I'm considering this where my x can vary between A to B. How would you interpret that statement? That would be integral A to B f of x dx. If x is a continuous variable and it can take continuous values between A to B, the probability is simply the integral of A to B f of x dx, or the area under this curve. Okay, so if I write probability of A to B, that is integral A to B f of x dx. What is the probability that x takes any value between minus infinity to infinity? That will be minus infinity to infinity f of x dx. It's like asking what is the probability that x will take any value? What is your answer? You don't have to do math to say this. Infinity. Not infinity. I'm saying x can take any value. Any value is the favorable outcome. In that case, what is the probability of x taking a value? 1. It's like saying if I show up for the game, that's counted as a victory. Right? That is 1. Okay. So you have this notion, or you have this quantity probability density function f of x probability value of, let's say, a less than or equal to b, or less than or equal to x less than or equal to b. This is a to b f of x dx. Cumulative probability that is x assuming all possible values from minus infinity to, say, for example, a. That would be minus infinity to a f of x dx. This is not totally new. I don't want you to think that you are seeing this for the first time. You did see the discrete distributions, right? When we did discrete distributions, so this is for continuous distributions, and for discrete distributions, you had probability, P of xi equals ni divided by nt. You didn't have a density function, but you have a probability expression which sort of rolls both of these into one. You also looked at cumulative probability, which is f of xn equals summation I equals 1 to n P of xi. Here you have integral because it is a continuous variable, and here we have summation. That's one difference. We use lowercase to represent continuous variables, whereas we use uppercase to denote discrete variables. Okay. The parallels continue. There are more parallels. Okay. So you think about average or mean value. For a discrete distribution, how would you get the average value of x? Suppose x is your random variable. How will you get the average of x? We talked about this when we did histogram. It's like asking I equals 1 to n x times or xi times p of xi. So it's like asking, I have a dice. I'll give the example. A dice. Okay. What is the average value while rolling a fair dice? What are the possible values? You tell me when you roll a dice. 1, 2, 3, 4, 5, 6. Okay, it has to be either of these. And they all have equal probability, 1/6. So if you get a 1, the chance of getting a 1 or a 6 is the same. But what is the average value of the throw? Suppose you did, like, let's say, four rolls. You get 1, 4, 2, 6. What is the average value of these 4 rolls? 5, 7, 13, 13 divided by 4. 13 divided by 4 is 3.25. Right, 3.25. It's, if I tell you the average is 3.25, that is sort of unsettling to you because you know that it can only be discrete numbers. But what it means is if you did enough trials, the average will come out to that. Can you compute the average? So you can compute x bar equals value of x and the chance of x. So this is summation. This is basically 1 multiplied by 1/6 plus 2 times 1/6 plus 3 times 1/6 and so on, 6 times 1/6. So what is the value? 1/6 multiplied by 3, 6, 10, 15, 21. This is 3.5. Why is it 3.5? Because the way the probabilities are weighted and the possible values. Okay. Now, if I ask you the question, what is the average value of x when x is a continuous random variable? So if you have a continuous random variable, what is the average value or mean? That would be x bar, which would be from minus infinity to infinity, the range of x, x times f of x dx. This is the value of x, exactly like here. And then you have to multiply by the probability, which is this. So this is the value of x or possible value of x. And this is the probability of that value occurring. So you're going to do a lot more integration. That is, when you do continuous random variables, there is a lot of integration involved. But we try to minimize the pain as much as possible by some mathematical tricks. Okay, we have lookup sheets and graphs that you can read out instead of having to do the integration every time. So I'll teach you those tricks. So this is average for a discrete random variable and a continuous random variable. Okay. I'll let you write up to here. So we saw the basic ideas, like sort of like a two-column comparison between continuous and discrete. What is probability? What is cumulative probability? What is average? Next thing we want to see is what is standard deviation. How do you calculate standard deviations for the two types of distributions? So I'll write standard deviation or variance. So coming back to our example about x bar, if I think about xi minus x bar, let's say for I equals 1, 2, 3, 4, 5, 6. What is my average? 3.5. So for I equals 1, xi minus x bar is 1 minus 3.5 or minus 2.5, minus 1.5, minus 0.5, 0.5, 1.5, 2.5. How will you get standard deviation? You will square them and add them. So this would be standard deviation would be xi minus x bar squared sum from I equals 1 to n divided by n minus 1 squared. That is standard deviation as we always do it. This is easy to imagine if you have only few outcomes. But if you have many outcomes, the way we write it is xi minus x bar multiplied squared multiplied by the probability of xi summed over I equals 1 to n divided by n minus 1. So this is the formula for standard deviation for discrete distributions. This is the probability. I know you might be thinking an example here would help, but there are just a few more concepts. Once I get through them, I'll get into examples. Okay, so for continuous random variables, we have the variance sigma squared equals minus infinity to infinity x minus x bar squared f of x dx. Same idea. This is the deviation squared, and this is the probability of that happening. So we generally say standard deviation is equal to square root of the variance. That is square root of sigma squared, or we call it sigma. For your quiz, the kind of problems you're going to expect, you could expect are given one, I mean, there are two problems. One is going to be either on discrete distribution or continuous distribution. The other problem is going to be related to students t distribution and uncertainty, which I'll get to probably next lecture. Okay. But between these two, you can expect at least one problem, which will either be this or this. Okay. And the kind of problem is like, it goes on like this. Let me give you like an example problem. Suppose x is the number of road accidents in a highway. Okay, in a highway, if the average rate of accidents is 400, not 400, maybe it's too like 40 per month, calculate a probability of no more than 30 accidents in a period of 20 days. And when I say 40 per month, we'll assume a month is equal to 30 days. What is the probability of no more than 30 accidents in a period of 20 days? This is the kind of question you can expect at your quiz. Okay. So how will you start? It doesn't say anything about the distribution. What distribution does this X follow? I didn't say. But I did mention something about accidents, and I said rare events are usually modeled as Poisson distributed. Poisson distributed. So first we'll assume X is Poisson distributed. If that is the case, probability of x taking a specific value is given by e power minus lambda, lambda power x divided by x factor. What is lambda? Lambda is 40 accidents, 40 accidents in a period of 30 days multiplied by our window of interest, which is 20 days. So lambda is 2/3 of 40. How much is 2/3 of 40? Can you tell? What is 2/3 of 40? $26.6666. So lambda is 26.6666. I think maybe I keep that number too high, so maybe I should say four per month, so that it makes little more sense. 4 per month, so 1.33. So 2.67 is lambda. And then we'll say no more than 4 accidents. Sorry, yeah, 4 accidents in a period of 20 days. So how will you convert this statement into a probability? That's the first question. If x is the number of accidents, how will you translate this into P of x? What is no more than 4? How do you translate it? No more than 4 means x cannot take a value more than 4. Maximum possible is 4. So x is less than or equal to 4. And what is probability of x less than or equal to 4? That would mean it can take 0, it can take the value of 1, it can take the value of 2, it can also take the value of 3, it can take the value of 4. All these are possible. So this is nothing but the cumulative probability of x equal to 4. What is the next step? If this is the probability of x assuming a certain value, I want the sum from 0 to 4. On. Is it something's not clear? Please tell me. What is P of x greater than or equal to 4? That will be summation I equal to 0 to 4. X equal to 0 to 4. Probability of x. What is P0? E power minus lambda, lambda power 0 divided by 0 factorial, or this is just e power minus lambda. P1 will be e power minus lambda times lambda power 1, or just lambda. P2 will be e power minus lambda, lambda squared by 2 factorial. You can write P3 e power minus lambda, lambda cube by 3 factorial, P4 is e power minus lambda, lambda to the 4 divided by 4 factorial. So, if suppose the question were probability of no more than 4 accidents, this is the translation. What if the question is no more than 2 accidents? Probability of x less than or equal to 2. If the question is probability of exactly 1 accident, then what will you come to? X equal to 1. And if you are the emergency vehicle driver planning your month, kind of asking what is the probability of no less than 3 accidents? How will you translate it? No less than 3 accidents. Probability of x at least 3. Okay, so this sentence that appears here, translating it into a mathematical statement is the most critical thing. If you do that correctly, I trust you that you can do these calculations. You can get your calculator out, compute these values, plug them in, you can do all that. But this is the critical skill. Okay, reading the problem and converting it into a probability. So for the exam, you can expect a problem like this, or something that is related to continuous variables, which we are in the process of discussing. Okay. This making sense to you? How do you read the problem is everything. Okay? All right, coming back to continuous. The first type of distribution we want to look at, the really simplest distribution, we call it uniform distribution. Here x has the same chance, same probability of us taking any value between A and B. So if I say this is x, this is A to B, I am saying x has the same chance of taking any value between A and B. How will you represent that as a graph? If f of x is just constant across the interval, how will the graph look like? Flat line, right? So if this is f of x. Okay, so this value here, how do we get this? How do we know the y-axis value? We know the x-axis starts from A to B, and we know it is flat or it is uniform. But how do we get the actual value? What do you know about probability densities? You know that the sum of all possible values should add up to 1. Okay. In this case, even though this function looks like a flat line between A to B, you can just define the function to be f of x equal to 0 when x is less than A and 0 when x is greater than B, and then some value C when x is between A and B. This is some unknown value C which we are going to determine. Okay, so I can write this integral into 3 parts. can write this integral as minus infinity to a f of x dx plus a to b f of x dx plus b to infinity f of x dx, and all of these should add up to 1. Don't be fooled by the integration signs, it's all very simple stuff. We'll make it very, very simple. What is the first integral? 0, because the function is defined as 0 for x less than a. So this is 0. For the same reason, this is 0. So you have integral a to b c dx, because we assume that it takes some unknown value c, okay, in the middle, and this is c dx equal to 1, or you can write c is 1 over b minus a. So this unknown or this value of c is 1 over b minus a, or 1 divided by width of the interval. When we did the binomial random number generation or Poisson random number generation, we relied on a uniform random number. That is this uniform random. Basically, at that point, I didn't introduce it, but this is the same thing that previously appeared. A uniform random number. Can you calculate or can you figure out what is the cumulative probability distribution look like? First of all, for a continuous random variable, what is the meaning of cumulative probability?
Probability of all the options added up.
All the options add up until a certain point. So if I write f of x, it's like writing minus infinity to x f of x dx. It's like this x is like a slider. Listen for 1 second. Listen. This x is like a slider. So if I just start counting from minus infinity all the way to up to here, okay, then the probability includes a lot of zeros, and then suppose this is 30% of the way between a and b, this includes this 30%. If I place the slider at 50%, everywhere from minus infinity to 50%, so this value will be 0.5. And that has a special name. What is something that is exactly halfway in your data? What is the value below which 50% of the data lies? Median. Where else do you encounter median? Or not that median. Maybe that median also divides the road, is supposed to divide the road into 2 equal halves, but we're talking about median as it appears in statistics. Where do you hear it in the news or your other courses? Taxes, okay, what about taxes?
Like, I was meeting all.
Actually, in the US, median has no meaning in taxes because it's the first 0.1% and then the rest of everybody. So median has no sense. But the place where it makes most sense is median home prices. If when you all start buying homes, you will inquire what are the median home prices in a neighborhood, and you want to go into a neighborhood where the median prices are reasonably high, so that your home will also have a good value. And not only that, when you go out and start seeking jobs, you will see these job reports saying the median salary for graduates in this period of time is 62,000. Then you think, am I above the median or below the median? Am I getting an offer which is competitive or less than the median? You'd start thinking about those. Anyway, median is the value that divides the data into half. So this cumulative distribution function, okay, is essentially something, if I ask you to calculate, at the midpoint, how much of the probability is contained? How will you do that? That would be A to A plus B over 2, 1 over B minus A dx. So I should write 50% or probability contained up to the midpoint. So the midpoint between A and B is A plus B over 2. So if you do the integration, this is A plus B over 2 minus B divided by B minus A. How much is this value? This is B minus A divided by 2 divided by 1 minus B minus A. Whatever A and B are, this is 0.5. Okay. So a uniform distribution is sort of a very convenient model. It's a convenient model, a good model for quantities that are equally likely to us to take values in a finite range. At the end of the day, these distributions are all models for quantities. They have to describe some quantity. Can you plot f of x for any x? What is f of x? Minus infinity to x, f of x dx. The distribution function integrated from minus infinity to some specific value up to that point. That is like saying from the beginning to some value, not all the way, but to some value. Okay. For a uniform distribution, what is f of x? F of x is 1 over b minus a, where x is between a to b. So this f of x is nothing but a to x 1 over b minus a times dx. Or this is x minus a divided by b minus a. Can you plot this on a graph where you have here is x, it varies between a to b. Can you plot this function? First of all, what kind of a function is this? Look at the x and y. It's a linear, right? It's a linear which starts at x equal to a. And if you put x equal to a, f of x is 0. So it starts here. If you plug in x equal to b, what do you get? 1. 1. X equal to b gets you 1. So it varies between 0 to 1. And it is a linear. So 2 points, connect them with a straight line. This is nothing but f of x equal to x minus a divided by b minus a. So when you took something that is constant and integrated once, you got a linear. Can you say the reverse? If you take f of x and take its slope of f of x gets you the probability f of x. That is f dash of x equal to the probability density function. That is just the way they are defined. You can just look at this and say that. You can look at this definition and say if this is true, then f dash of x should be equal to f of x. You can simply say that for any distribution, not just uniform distribution. Do you feel ready to see the normal distribution? Like, do you have any questions? Do you want to ask something? So the second distribution in our list, normal or Gaussian distribution. So when we saw uniform distribution, what is the main feature of the uniform distribution? Main feature of the uniform distribution. If you have to say one thing about it, it's flat. It's the word is uniform, right? It's uniform in a given interval. Or if you look at it and interpret it, it's like saying all the values have the same chance of occurring. Normal distribution is unlike that. Normal distribution displays or has a central tendency where some values displays a central tendency, some values are more likely than others, like some occur more frequently, some occur less frequently. Okay, what Gauss did is to come up with this function f of x equal to 1 over sigma times square root of 2 pi exponent of minus 1/2 x minus mu by sigma squared that correctly describes the data. That is, if you had underlying data that looked like this, what Gauss did was to come up with the correct function that describes the data and allows you to, instead of dealing with a lot of numbers, it allows you to work with this function where mu is the mean and sigma is the standard deviation, or sigma squared is the variance. So this is the probability density function for the normal distribution. And what would be the, can you plot the f of x, which is the cumulative probability distribution? So if I say the cumulative probability distribution, we'll call it f of x uppercase. This is minus infinity to x f of x dx. I forgot to mention x can vary between minus infinity to plus infinity. Any range is okay. Any real number is fine. Before we start doing some calculations, let me ask you some questions. Okay. If I ask you, what is the value of minus infinity to infinity f of x dx in general for any distribution, what is your response? 1. This is by definition, right? By definition. Okay. So if I ask you, what is the value of x, okay, for which this distribution is split into exactly two halves? That is the value of median. The question is, how do you figure out the median for the normal distribution? I'm just stating the problem. I'm not asking anything yet. How do you figure out the median for the normal distribution? That is my question. The question making sense to you? Okay, this is the distribution. It follows a bell curve. X can vary from minus infinity to plus infinity. Where do you locate the value of x which divides that graph into two exact halves? So in general, what is a to b f of x dx? Like when you're doing integration, that is area under the graph, right? So now I'm asking you the question. Right, redraw this. Redraw this. Okay. This is area under the graph. The entire area. This is 100%. That's what the first statement is. It's like saying the area under the graph, if you consider it to be 100%, what value of x will divide that area into exactly half and half? You don't have to stop at half. You can ask the question, what is the value of x to the left of which lies 90% and to the right of which lies 10%? Okay. You're with me so far? All I'm asking you to do is look at a graph and talk about area under the graph. Okay. The other big calculation is the probability that x takes values in the range a to b is. What is the probability that x varies between a to b? I told this some moments ago, but can you recall or can you tell me based on what we have seen so far? We know that area under the graph equals probability. So in that sense, what will be the expression for this? What is the probability of x taking a specific range of values? Want to tell something?
In the graph,
Yeah, if suppose I'm interested in x taking a range of values between a to b, how will I write an expression for that? Yeah,
We talk about the point.
from a to b.
Yeah.
So can you turn that into a like an expression based on the two ideas we saw here? So, but when you say bounds, are you saying a to b? What goes inside?
Function.
F of x dx. I saw that I said this a few moments ago. That is, the probability of x taking a range of values is a to b f of x dx. Okay. So if I have a lookup table for area under this graph plotted from minus infinity to different values of x, I can write this down immediately. I don't need to do integration again and again. That is, the whole point is to avoid integration because it's very tedious and time consuming. So look at this. This is minus infinity to x f of x dx. How will you interpret this integral? This is like writing. This is minus infinity to some x. This is to the left of that x. Would you agree? Okay. If I take this integral, I can write it minus infinity to b minus infinity to a f of x dx. Can I write it this way? Just splitting the integral as like saying, this is this like saying, here is my bell curve, here is a to b, which is what I care about. I can say this area 1 minus this area 2 is my quantity of interest, 1 minus 2. If I had a lookup table for, this is nothing but f of b minus f of a. So what is the utility of this cumulative distribution function? If you have it tabulated, the difference between two values gives you the probability of x taking that value. So this is nothing but f of b minus f of a. If we had a tabulation of this cumulative density function, we don't have to ever do integration. Do you see that point? So next thing I'm going to pop up is the cumulative distribution function plotted as a table or given as a table. Once we see that, we can start asking questions or start answering questions. Are we together so far? If we have a table of the cumulative distribution function, we can evaluate any probabilities that we want. That's the idea. Okay. So okay, so let's start with an example. Let us say we have a distribution with mu equal to 0 and sigma equal to 1 or sigma squared equal to 1. So in this case, f of x equal to 1 over square root of 2 pi exponent of minus x squared time divided by 2. Okay. So your goal is to compute what is the probability that x takes values between minus 1 to plus 1. That is your goal, which is minus 1 to plus 1 f of x dx, area under the graph, which is equal to f of plus 1 minus f of minus 1 using CDF, cumulative density function or cumulative distribution function. This is another type of problem you could expect. Given a distribution, a value of mean and variance, what is the probability that X will assume these values? X lies between -1 to 1. It translates as probability of -1 to 1 of X, which is the integral, which is the cumulative distribution function. Okay. So now let me bring up the textbook here. All right. No need to write, okay? When I start it in the next lecture, I'll give a recap. I'll rewrite some of the things to reinforce. So take a break and talk to me. We have 8 minutes, okay? Let's see if we can get through this. All right, so now we have a table, okay? Pay attention, no need to write, look up, okay? I need to share my screen and make sure this is getting recorded. All right. Look at the top there. P of Z1, what I call as X, they are calling it as Z1. P of Z1 is 1 over square root of 2 pi, 0 to Z1 minus exponent of minus beta squared over 2 is d beta. The fact that they use beta is completely irrelevant. You can use t or x or whatever value. Okay. So this table here, it is a calculation of this integral, this quantity. 1 second. So if we calculate 0 to z, 0 to z, 1 over square root of 2 pi e power minus beta squared over 2 d beta. That is what this table calculates. Just assume that they have done numerical integration to get you these values, so you don't have to do it. If I put z equal to 1, how will you read this table? You look down, look for 1, the value is 0.3413. So if I say, if I'm interested in 0 to 1 e power minus beta squared over 2 square root of 2 pi d beta, this value is 0.3413. You can read from the table, 0.3413. Okay. If I want 0 to, let's say 0.5, can you read and tell me? 0.1915, and it's given to 2 decimal points. Suppose I wanted 0.55, what will be the value? If I want 0 to 0.55, 0.5 is here, 0.05, so 0.2088. So this is the lookup chart. To understand the lookup chart, you need to know what is being calculated or tabulated, which is 0 to z, this integral. Okay, but what do I want? I want -1 to 1 f of x dx, which is -1 to 1 over square root of 2 pi e power minus x squared over 2 dx. I told you it's completely irrelevant whether you call it x or beta, because it's just a integration variable. So this integral, you know that this function is an even function. So you can write this is 2 times 0 to 1 e power minus beta squared over 2 square root of 2 pi d beta. And what is the value of this integral from the lookup chart? Zero to one. That is, if I want 0 to 1, it's 0.3413. So this is 2 times 0.3413, or this is 0.6826. I wanted between -1 to 1. I reduced it to something that can be used or solved using this lookup chart, which is you have to always make it as 0 to something, 0 to 1. 2 times 0 to 1. Okay? With me so far? Yeah? Suppose I want -1 to 0.5, same thing, 1 over square root of 2 pi e power minus x squared over 2 dx. What will I do? What will I do to reduce this problem into something that can actually be solved with this lookup sheet? You know the answer and you just don't like me, or you don't know the answer. Or you want to say something but you are not sure. If you are not sure, I strongly recommend you say something. Don't worry about it. Okay, I am interested in probability of x taking values between -1 to 0.5. You're with me? You're with me? And this is -1 to 0.5 f of x dx. You're with me? This is -1 to 0.5, 1 over square root of 2 pi e power minus beta squared over 2 d beta. You are with me? This is -1 to 0 of this thing plus 0 to 0.5 of the same thing, of the same function. We are together? This table or this lookup chart is meant for anything in the form of 0 to a positive number. 0 to a positive number. Can you look up and say what the value of this integral is? Let me maybe zoom in for you. Can you see now?
Yeah,
0.1915. Everybody agrees? 0.1915. But what about -1 to 0? Remember this bell curve, if this is x equal to 0, okay, this is f of x equal to 1 over square root of 2 pi e power minus x squared over 2. What about this jumps to you? About x equal to 0, yes. That is, you want to say this is 0 to 1, not -1 to 0. You are correct, but why? Why do you say that? Tell me the answer and everyone can listen. Yeah, flip the limits, yeah. And also you inverted a sign. Say that to me. It's like this function is symmetric about.
so 1 would equal 1. Symmetric.
Right, when you say -1 to 0, this area is exactly same as between 0 to 1. It is symmetric about 0. You see that? Everybody sees that it is symmetric about 0. So what is -1 to 0? You can easily do that substitution, let's say you write gamma equals minus beta, which will become 0 to 1 e power minus gamma squared over 2 d gamma divided by square root of 2 pi, which is in the form that this table is made for. What is the value of this from the table? 0 to 1 of the integral. 3413, right? So this is 3413. So the total probability is the sum of these two, which is 8, 2, 13 carry over 1, 4, 5, 53.28. So all the problems related to normal distribution, what we are going to see is an exercise in reducing your problem into something that can be reduced or solved using this lookup sheet. This is posted on Canvas. You can download this handout and you can use it to solve problems. And we are just getting started. Next lecture, I'll give more details on this. Okay, thank you.